Everyone. Hello everyone, can you hear me? Sorry for being late. Can you hear me? I'm checking the live chat. If you can't hear me, can you please drop a yes in the live chat saying you can hear me? Just so I know I can continue. Hi Pawan, how are you? Hello Rahul. Good to see you back. Yes, awesome. Hi Harshad. So good morning everyone. So I'm Sai Avinash, and in this class I'll be teaching combinatorics, problem solving in combinatorics. They're two really standard problems, but I'll explain how to do them. And so a little about myself. I'm Sai Avinash. I'm in a studies fee at Google Dublin and currently working there. I'm All India rank 4 in CodeChef. I'm a 7-star coder there. And I'm actually International Master at Codeforces. I'm currently a master. I'm an SD intern at Uber, and I'm also snagged on finalist. So the subjects that I take are discrete math, dynamic programming, and graphs, and a lot of other competitive programming topics that you'll be seeing soon. So use the code SciLive to get 10% off on the Unacademy Unacademy Pro subscription. So what's the career as a developer subscription? It contains interesting shows covering a variety of topics. It shows you live problem solving with just like 999 for 1 year. Thanks Pawan for that. So who should buy the subscription? People who want to learn continuously throughout their career, like whether related to computer science or in general. It's like a Netflix for computer science, but yeah, it's taken by one of the best programmers of the country. And I think if you are going to seek learning throughout your career, either as a student or as a developer, that would be a good subscription for you. And it's just $9.99 per year. And use the code SciLive there to get an additional 10% off on the Unacademy Pro subscription. So there's going to be live problem solving and many more. So the CodeChef Apprentice. So this show is taken by me. It goes live on every Saturday afternoon at 2 p.m. It starts on 14th August. So it's taken by me. The show is like I'd pick a mentee, like I pick a student, and then I would ask them what their blockers are in general and where they're getting blocked and which point in their career they are. And I would help them. I would help them very closely in how they could progress. I would basically mentor them for an hour, and in the end, I would make them solve a problem on their own. Like I would give them hints so that they could come up with their solution on their own. The problem that was picked by them itself, the problem that they couldn't solve initially, and I would make them solve the problem on their own, and I would show how practice would help them get better. So this course has already started on 14th August, sorry, and it's taken by me, and I've already described about me. I work at Google and I'm a 7-star coder at CodeChef. So there's that. So one sec. Oh, I think I've chosen the long slide deck. One sec. Oh no. Oh yeah, never mind. Yeah. So do follow us on t.me/codebursofficial. That's where live updates on channels are gonna happen. Like whenever a new video comes up, that's where it'll be shown first a few days in advance. So if you subscribe to that, you'll get notified early so you can learn quickly. So if you think this content is going to be useful to you, do like this video and share it with your friends so that the knowledge is spread, as I said. And if you haven't subscribed already, what are you waiting for? All right. So Harshad asks me, are there any prerequisites for this class? my first class. Ideally, there are a few prerequisites, like you need to know what binomial coefficients are. So if you know binomial coefficients and the path, like the number of paths from 0, 0 to m, n, and like you need to know basic binomial, basic combinatorics, because that's what I've taught in the previous 2 classes. If you really want to like learn complete combinatorics, I would not complete, like the real basics of combinatorics, I'd suggest you to go to the first 2 classes, like of combinatorics, basically the last 2 classes, the combinatorics 1 and combinatorics 2. I've explained that clearly about a few binomial theorem concepts. And after that, I'll be coming here, like this would use a bit of that. But if you know that already from high school or something, then that's cool too. You don't need any prerequisites, but you can definitely give this class a try. All right. So if it's, yeah. Any good CF blocks to learn everything about combinatorics suggested by? Honestly, I don't think there's going to be one CF block covering all combinatorics topics. Combinatorics is a huge topic, and yeah. I don't recall seeing any CF block which contains all combinatorics topics. Best you can do is keep solving several problems. Like there's no shortcut CF block. Yeah. Okay, Harshad Banatin was great. So let's get started without any delay. 1 second. I'll just open Sketchpad. All right. So the first problem. Count the number of valid bracket sequences of size n. Count the number of valid bracket sequences of size n. Now, what is, I don't want subscription. Nope. What is a valid bracket sequence? What is a valid bracket sequence here? Hi, Sumita. Educator has a great combinatorics block and questions. Could you paste that here for everyone else to see it? So, what is a valid bracket sequence? This is a valid bracket sequence. Empty string is also a valid bracket sequence. This is a valid bracket sequence. This is a valid bracket sequence, and so on. All right, we know examples. What is the definition of a valid bracket sequence? So it has a recursive definition, and by recursive definition, I'll tell you what it means. So S equals, so basically, empty string is a valid bracket sequence. Empty string is a valid bracket sequence. And this is the first point of the definition. Second point is, if S is a valid bracket sequence, then open bracket S, close bracket is also a valid bracket sequence. Third point is, if S is a valid bracket sequence and T is also a valid bracket sequence, then S into T is a valid bracket sequence. All right. So let's just take examples. For example, how do you generate a valid bracket sequence? This is a valid bracket sequence. Since this is a valid bracket sequence, using rule number 2, we get this is a valid bracket sequence. Again, if you want to use rule number 2 again, you get this is a valid bracket sequence. Now, if you want to use rule number 3, it's basically, we can take S equals this and T equals this, and we get as a valid bracket sequence. This is also a valid bracket sequence. So basically, concatenation of 2 valid bracket sequences is a valid bracket sequence. When number of open brackets equals number of closing brackets, it's not always true. There's another condition on top of that. For example, this is not a valid bracket sequence because this does not follow any rule. And it's not a valid bracket sequence in general, as you can see. All right. So one rule is, like, if you want to make another rule, how do you check if a number is a valid bracket, of a bracket sequence is valid? So we are opening a bracket, then closing a bracket, opening. Now, one definite condition is number of opening is equal to number of closing. Opening equals number of closing. Second, there should be no point in the string that the number of closing brackets is more than the number of opening brackets, which is, for example, here the number of closing brackets before this is 0, number of opening brackets is 1. Here I'll just write opening, closing, 1, 0, 2, 0. Here 2, there's 1 closing bracket. Here there is 3, 1, 3, 1. Here the number of opening brackets is not equal to the number of closing brackets. So what we do, we add 2 more, and then we see here that 3, 2 closing, 3, 2, 3 closing. So this is a valid bracket sequence. Oh wait, there's another one. Wait 1 second. I missed something. This is 4 by the way. 4. You need to have 3 brackets. 4, 4, 4, 2, 3, 4. All right. Awesome. Now what do we need? So we'll make our own rules from that. So first rule is closing equals opening. Closing brackets equals opening brackets. Second one is at any point the number of opening brackets should always be greater than or equal to the number of closing brackets. The number of opening brackets before it should be greater than or equal to the number of closing brackets. For example, here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The number of opening brackets is 1, 2, 3, 1, 2, 3, 4, 5. Closing brackets is also 5. But here, at this point, if you look at this point, the number of closing brackets is 4. Sorry. Closing brackets is 4. Number of opening brackets is 3. Since closing brackets is greater than number of opening brackets, this is not a valid bracket sequence. And what is the intuition of a valid bracket sequence? For every opening bracket, there is a corresponding closing bracket. For example, so this is a bad sequence. So let's take a good sequence and see what it means, what a valid bracket sequence means. So So this is a valid bracket sequence. It means for every character, for every opening bracket, there is a corresponding closing bracket. This is a corresponding closing bracket where everything from inside the closing bracket, starting from the opening bracket to the closing bracket, everything inside it is also a valid bracket sequence, right? All right. So what this means is, we can see that this is a pair. This is a pair. We can see that this is also a pair. This is a pair. This is a pair. This is a pair. And since all of them inside are valid bracket sequences, there's a bracket here as well. This is also a pair. All right. So the condition for checking a valid bracket sequence is that at any point the number of closing brackets before this should be less than or equal to the number of opening brackets. The opening brackets should always be more than the closing brackets. Why? Because if the number of opening brackets is less than the number of closing brackets at any point, that means there's the closing bracket before this which is not matched before to any opening bracket, right? Is that clear? Any doubts so far with respect to bracket sequences? Any doubts? Wait, I'll just stop. Any doubts? Please point it in the live chat. All right. For example, if you take 1, 2, 3, 4, 5, 6, 7, 8. Yeah. Now in this is matched with this, perfect. This is matched with this, perfect. This is also matched with this, perfect. Now this bracket has nothing to be matched with. This is this is a bad valid sequence, bracket sequence. So because this has nothing to be matched with. So that means at any prefix, no bracket should be matched with, like, at any prefix, the number of opening brackets should always be greater than or equal to the number of closing brackets. The code is very simple to check. I'll just write it in 3 minutes. This is not a part of the combinatorics course, but I'll just write it. Most of you already know. Mohit, you have any doubts? Could you please be more specific? This was the okay. Bool. Check. Bracket. String is. I'll just write. Int closing equals 0, opening equals 0 for int I, for char u equals uns, if u equals opening plus plus, else if u equals closing plus plus, else if there is some other character other than the opening and closing, return false. Now, if at any point if opening is less than closing, return false. And in the end, if opening equals closing, return true. Meaning the number of opening brackets should be equal to the number of closing brackets. If this is not true, then return false. That's the code, simple. Check bracket sequence, take a string. The number of closing brackets should be equal to the number of opening brackets in the end. And at every point, the number of opening should be, or you could write this as, yeah. So if opening is less than closing, oh shit, sorry, sir. Apologies. This is my bad. Is this clear? I'm sorry for that. It should be clear now. Oh, is this clear now? I'm so sorry. I'll write it again. Is this clear? Can everyone see it now? Can you all see it now? So, check bracket sequences. Basically, I'm keeping a track of closing brackets and opening brackets as I go one by one from the left. Okay. Let me know if it's clear. Okay, increasing the font size. Is this clear? Yeah, I increase the font size too. So, I'm keeping the track of opening brackets and closing brackets. All right. Rahul, which part do you want me to explain again? I'm keeping the number of opening brackets and closing brackets. And at any point, if it's opening, I'm increasing the opening, incrementing the opening value. And if it's closing, I'm incrementing the closing. If there's some other character, I'm returning false. At any point, if opening is less than closing, I return false because it's not a valid bracket sequence. Rahul, could you be more specific at which point you want me to explain again? And if opening bracket should be equal to the number of closing brackets in the end, return true. If nothing satisfies, return false. All right. Yeah. Okay. So I just explained the code. So any doubts with the code, please let me know. Any doubts? I'm just looking at the chat. So any doubts with the code, please let me know. Clear. Awesome. All right. So this was just to explain what's the deal with it. Now, how do you compute how many valid bracket sequences are there? How do you compute how many valid bracket sequences are there? How do you do it? So we know that. Let's take a bracket sequence here. Right. Yeah. So yeah, Pawan, the solution is alternative to the stack solution. The stack solution doesn't require any extra space, does require an extra space, but this one doesn't require any extra space. It's an O1 extra space solution. Yeah. But the stack solution does give you what the pairings between the brackets are, like which bracket maps to which bracket. It gives you that. So Neelam Shetty, checking opening equals closing, and opening should be greater than closing, greater than or equal to closing at every point. That's enough. And you also need to check if there are any extra characters, but if that's not given in the question, you don't need to check that. I was just being careful. So just look at this bracket sequence. What is happening here? If you look at it closely, this is one bracket sequence and this is one bracket sequence, right? So a bracket sequence of n can be recursively called as like bracket sequence of Sn minus, it could either be Sn minus 1 or it could be Sa Sb. So a bracket sequence of size n can be written as a bracket sequence Sn minus 1 covered with Sn minus 1 covered with the bracket. For example, bracket sequence of this. Yeah, at every moment opening should be greater than or equal to closing. Greater than or equal to closing, not greater than. So if look at this is a bracket sequence of size. Like I'm taking n as Sn is the number bracket sequence of size 2n, okay? The number of basically opening brackets, not counting both of them, okay? That's the thing. So basically S2 can be or we need to count the number of valid bracket sequences where the number of opening brackets is 2. So what do we do here? So where do we even start? So in such problems, what you do is you think recursively. You try to think recursively because the definition itself is recursive. You try to think recursively. Let that be one of your ideas when you're coming up with a solution. Okay. So now what you do, a valid bracket of size 2 is or okay, size 3. It could be either or, like I'm just covering S2 with this, or it could also be right. It could also be isn't it? Fair, right? It could be both of them. Awesome. Now, so at every moment, opening should be greater than or equal to closing. Yeah, give me a minute. Now, so we can see that. Let's, the initial part, like what we do is we define it recursively and calculate it that way itself. So what is this? This is basically S2, right? This is also S2. Or this is S0, S2. This is S0, S2. Yeah, let's not consider all types of brackets. We're just considering only the curvy brackets. All right. Now, how we calculate is, we calculate it recursively. Let's say the answer for n is equal to an. All right. Now, an is equal to an minus 1 because an minus 1, why are we taking an minus 1? Because all bracket sequences of size n, like of basically a size 2n here. A answer of n represents size 2n because we're just taking opening brackets. All bracket sequences of size 2n can be directly computed by covering a closing bracket or size Sn. We just saw that Sn minus 1, right? So the number of bracket sequences of size n would be at least the count of number of sequences of size n minus 1. Note that when I'm saying size n, it means the bracket sequence of length 2n. Okay? Plus, there are going to be many more. Is equal to, now, it could be this and Sn minus 1, or S1, Sn minus 2, and so on. For example, I'll just list down them, for example. Oh man. For example, yeah, Pawan, feel free to share your solution there. So, Sn equals bracket, close, take a valid bracket sequence of size n minus 1 and put it inside Sn minus 1, or, and put nothing here. We can call that S0, or like this, basically S0 is an empty string. Now, we put Sn minus 2 here and put S1 here. For example, if you want to calculate S4, we can take and an empty string here. This is basically S3, and we're covering it with a bracket. That's basically this. Now, Sn could also be Sn minus 2 into S1. Sn could also be Sn minus 3 into S2. So basically, this is an example for this is this. So inside there's S2, S4 minus 2 is S2, and outside there's an S1. This could be S1 inside and S2 outside. So that's an example. Yes, Bhagati is right. Yeah, Adarsha, I'll explain it. It's not clear, I understand. It's a hard topic to explain also, or even understand for that matter. So what I'm trying to do here is trying to compute I'm trying to compute all the valid bracket sequences of size n. So for that I'm trying to use a recursive manner. Say I know the answer for S1, like for example, I know what A1 is. A1, there's only one valid bracket sequence, so it's equal to 1. A2, there are two of them, 2. A3 is equal to, A3 is basically, what's A3? It could be this. We do it using the recursive fashion. Here there could be any of these two here inside, and outside there could be nothing. Like for example, here it could be, what did I do? I just covered this with a bracket outside. Or it could be like this also. Or what did I do here? Inside I put empty, like this is basically S0, S2. This is S0 and this is S2. You can see here. And another option is S1. There are 6 values here. Can you see this? There are 6 possible valid bracket sequences. Wait, 6. 1, 2, 3, 4, 5. Sorry, 5 valid bracket sequences. Got it? Is this clear so far? So one of them I computed with covering a bracket sequences over all bracket sequences of size 2 here. This is all bracket sequences of size 1 outside and then 2 inside, and so on. Is this clear? So, Baya, can we do like this? For every opening bracket, we can do count plus 1, and for every, yeah. In this way, you can count number of valid bracket sequences. Yes, that's correct. Yes, we can do that too. So, to make this clear, what I do is, so to compute answer of n, one option is, we saw that one option is covering Sn can be equal to Sn minus 1. So all bracket sequences of size n minus 1 can be covered with a bracket, and outside we can call this S0. Nothing is there, but we call it S0. Otherwise, we take Sn minus 2 here and put S1 outside, and take Sn minus 3 here, and take S2 outside, so on. So, how many bracket sequences can we form like this? This is basically a n minus 1 into number of bracket sequences of size 0. We can call that A0 plus number of bracket sequences of size a n minus 2. How many of them are there? A n minus 2, and outside we can put any bracket sequences of size 1. That's A1 plus here. What are we doing? We can take any bracket sequences of size n minus 3, a n minus 3, and we can take any bracket sequences of size 2 outside the bracket, right? That's why we multiplied by A2, and so on. Is this clear? Do you see what I'm doing here? Any questions here? Do you want me to re-explain anything? So, like, I'm not giving you the final answer yet. This is not the final answer. I'm just writing you the recursive, like, how can you represent the number of bracket sequences of size n as its smaller answers. That's how I'm trying to explain it. Is this being clear? Do you have any doubts so far? All right. So, to write this more formally, what I do is, no, it won't repeat. Why? Because that's a good question, right? So it won't repeat. Why? Because when we take here s n minus k, s k minus 1, basically, that's what you're doing, right? S n equals, for example, s n minus 1, s0, s n minus 3, sorry, s n minus 2, s1, s n minus 3, s2, so on. All right. Now, here the possibility won't repeat. Why? Because whatever the first bracket is matching to, it says it's matching to the first bracket is matching to, we are taking only what's inside that. And we know that the first bracket matches to a unique bracket outside, and whatever inside, it's fixed. So there's not going to be any repetition. No, for example, a n minus 1, a0, it won't match. I'll tell you why. So Vinay's question is, won't Sn minus 1, S0 match with S0, Sn minus 1? You can see it for you. Won't this like overlap? We can see why it won't overlap. For example, say n equals 3. Now n equals 3. S3 equals, S0 is basically an empty string. So S0 is basically an empty string. For example, S3 would be equal to empty string outside. And if you do it using this method, it will be different strings. Inside here it's empty inside the first bracket that's matching. Here it has two bracket sequences of size 2 here. Got it? This is essentially Sn minus 1, S0 is empty string, and this is writing Sn minus 1 and writing a single bracket before that. That's it, Sn minus 1. These two are different things. Got it? Is that clear, Vinay? All right. So, what did we discuss as the recursive solution? An equals a0. So let's write it in any way possible. So a n minus 1 into a n minus 1 can come completely inside the bracket into a0 outside the bracket, a0, plus n minus 2 can come inside, cover a bracket out of it, and a1 outside, a n minus 2 plus into a1, plus n minus 3 can come inside, 2 can come outside, and so on. an minus 3, a2, and so on. What would be the last number? It would be an empty string can come inside the bracket, a0 into, and n minus 1 can come outside the bracket. Which means like it's this and an an minus 1. Like Sn can also be this and Sn minus 1. This is the last case. The first case is this is empty string. We can call that S0. Here, first case is inside Sn minus 1, outside S0. And we're going through that. Like gradually we're taking one bracket outside, and that's how we're getting this. Is this clear, everyone? We can also see that the values add up, like a1 equals a0 equals 1. Like there is only one empty bracket sequence, right? You can't do anything much with that. a1, there's only one. Now a2 we'll do it using this method. a2 is equal to a1 a0 plus a0 a1. So you can see that this is equal to 2. a3 a0 a2 plus a1 a1 plus a2 a0. This is basically 2 plus 1 plus 2 is equal to 5. Is that clear? Remember, we got 5 bracket sequences back then as well when we enumerated them. If you want, if you want me to make this more clear, I can show this to you with an example. One second. So I'll tell you what bracket sequences of I'll list them down for you. I'll list them, each contribution I'll list them down. A0 is just empty string. This is just this one. A1 A0. What is A1 A0? This is outside empty. Inside this bracket there's a bracket sequence of size A1. Alright. This is inside the bracket sequence there's empty, and outside there's a bracket sequence of size 1. These are the two bracket sequences. Now here, coming here, A0 A2. Well, I'll just make this A2 A0 because that's how we computed it. And last one is A0 A2. A2 A0. So inside the first bracket sequence, there's the bracket sequences of right size 2. It can be either this, outside nothing, or this will be inside there's 1, outside also there's 1. This will be inside there's nothing, outside there's 2. We're just copying this here. We're copying this inside this. We're copying this again here, outside. Or this is bracket sequence of size 2. We're separating this. This is how we're separating. We're taking the first bracket matching inside and with the rest outside. So you can see that there's 1, 2, 3, 4, 5, and you can't make any more bracket sequences. If you want to list it down, you can. Is this clear so far? Is this clear? Any doubts? You all have any doubts? Vinay, Rahul, Pawan, Adarsha. If it's not clear, please let me know in the chat so that I'll explain this part more clearly. This is very important. So this is partly dynamic programming and combinatorics. So yeah. Vikash, could you explain which part do you need one more time? Which part do you need one more time? I would like to explain that part again. Could you others? Could you tell if it's clear, or is there any other part that you would like to be? Yeah. Okay. Okay. So what did we write here? Oh man. A3. You want me to explain A3 again? Okay. And how? Okay. So first I'll answer Pawan's question. How A0 an minus 1 and an minus 1 A0, how are they different? Now, okay, I'll give you two bracket sequences. You only tell me if they're different or not. So let's take this bracket sequence. Would you call these two bracket sequences different or not? Would you call these bracket sequences different or not? Sure, tell me in the chat. Yes or no? So yes, right. Because they're different. Like you can see that the second character is different. All right. Now this is produced by A0, A2. This, like for example, this is produced by A2, A0. How? You can see that inside the first bracket sequence there's an empty string and outside there's an A2. Outside the A2. Right. A0, A2. This is basically A0, A3, or like this is A0, A3 minus 1. And this, you can see that this is produced by, inside there's a bracket sequence corresponding to A2 and outside there's A0. This is basically A3 minus 1, A0. So this is A0, A3 minus 1. A0 and A3 minus 1 produces A0, A0, AN minus 1. In A0, AN minus 1, the first two characters are this, like the first two characters are opening and closing, that's it. But in AN minus 1, A0, the first and last are opening. First is opening and last is opening, and everything inside that is a valid bracket sequence. First and last are opening, and everything inside that is a valid bracket sequence. Whereas in A0, AN minus 1, only the first, inside the first valid bracket sequence, there is 0, there's nothing inside. And outside, you're putting an AN minus 1. Now you only told me that these two are different. And this is produced by AN minus 1, A0, and this is produced by A0, AN minus 1. This cannot be produced by this, and this cannot be produced by this. One cannot be produced by another. This can produce, this will produce and this will produce this. So this is how A0, AN minus 1 and AN minus 1, A0 are different. If anyone has a question with that. Pawan, is that clear? Yes, Vinay is correct. No. So Pawan, what is inside? No, in first A0 is not. In the first one, A0 is not bracket. So A0 is what's inside the bracket, inside the closing opening and closing bracket. A0 is what is inside the closing bracket. It's not the closing. It's not including the closing bracket. So let me make this clear again. So you need to get this correct. So here there is some AX. Outside there's some AY. So this, in this it means that X is 0, Y equals 2. In this, it means that X equals 1, Y equals 2. This does not mean X equals 1, and this does not mean X equals 2. It means X equals 1, whatever is inside, the bracket is not covered. Okay, got it? So is everything clear so far? Do you want me to cover A3 again? If you want me to cover A3, I can cover what A3, how A3 is really, how you can derive A3. If you want me to cover that. Or if you want me to continue how to compute this quickly, I can do that too. All right, Pawan got it. So Rahul and Vikash, you're asking for A3. Do you want me to explain it again? Or anyone else, like if you want me to clear it out, I can clear it. All right. So now we saw like how we could recursively explain, and I will just write out this formula here. AN equals A0 AN minus 1 plus A1 AN minus 2. Oh wait, I'll explain it how I taught it itself. Like I'll write the formula how I taught it in the reverse order. That's fine. Like anyway, it's cool. So AN minus 1 A0 plus AN minus 2 A1 plus AN minus 3 A2 plus so on till A1 A0 AN minus 1. Correct. Yeah, Pawan, that's correct. Yeah. So does anyone, is this clear with everyone? Is this clear? Where an is the number of valid bracket sequences of size n. So any questions with this? Like, is this formula clear? I'll explain how to code this. Like, some of you might find it difficult, so I'll explain how to code this from scratch, very basics. I'll explain it to code this. So any doubts so far? Is this clear? Is this formula clear? Do you want me to explain it again? Are you facing any difficulty with this? I understand, like, if you're just starting, it might be a bit hard to grasp. All right. Awesome. So let's just get to coding it. Let's just get to coding it. Okay. Okay. Okay, Suraj is asking me to teach it again. Suraj, if you're more clear, like if you're more clear about which part you want me to explain, I'll explain that part again. Like, which part is more inconvenient to you? I'll explain that part. So meanwhile, I'll just start writing the code. Long. Let's say and one second here. Yeah. So could you just write it out? Max n equals, say I want to compute till 1000. So long LL answer of max n. So now we have a recursive definition. Like if we have an, a0, a1, a2, a3, so on till an minus 1, we can get an directly. Right? We can get an directly. Right? So what this means is, like, if you have a0, a1, all right, you can rewatch. Okay. So if you have any doubts, drop it in the comment section. If you have a0, we can compute what a1 is. We can have a0, a1, we can compute what a2 is. A0, a1, a2, we can compute what a3 is. So on. Oh, Vinay, definitely. I'll show that too. So answer of 0 equals 1. Now for int I equals 0, I equals 1, I less than equal to max n, I plus plus. Answer for int j equals 0, j equals 0, j less than I minus 1, j less than equal to I minus 1, j plus plus. Answer of I plus equals answer of j into answer of I minus 1 minus j. That's what we did, right? Answer of n is equal to answer of 0 into answer of n minus 1, answer of 1 into n minus 1 minus 1, answer of 2 into answer of n minus 2 minus 1, so on, right? That's done. So is that clear? So basically we know answer of 0. So initially answer of 0 would be this. We wrote it as 1 because empty string, there's only one string. Answer of 1 would be like answer of 0 into answer of 0. Answer of 2 would be, you can see that 2 would be answer of 0 into answer of 1 plus answer of 1 into answer of 0. Answer of 3 would be 0 2 1 1 2 0. Is this clear? Is the code clear to everyone? When I'll do that, yeah. So it's clear, glad to hear that. Any doubts with this code? Answer of I equals 0. You need to initialize that, but since it's global, you don't need to initialize. But note that the number of valid bracket sequences of size 1000 can be really high. So usually they ask you to take modulo mod or something like that. This would overflow. So LL mod equals money 9 plus 7. So what we do here is answer of I since the answer can go really huge, you usually take mod. So if you understood this part, and if you know a bit of coding, you would understand this too. If you understood the formula, how we arrived at the formula, and if you understand a bit of coding, like if you know like very basic for loops, you know how to code this too. All right? Yeah, we're pre-computing it. Now, how would you generate? How would you generate a valid sequence? How would you generate? So, how do you generate? So we're gonna generate it. If you're gonna generate it, we also, if you can count it, turns out we can also generate it. Like we are counting it in a recursive fashion, right? So we'll generate it as well in a recursive fashion. Yes, it can be done using memorization too. I'll return this as vector of string. Generate valid bracket sequences of size n, int n. If n equals 0, return only one string, empty string. Okay. Otherwise, for int I equals 0, I less than n minus 1, I less than or equal to n minus 1, I plus plus. I'll tell you what I'm doing here. Vector string g equals generate n minus 1. String, sorry, inside bracket, sorry, one sec, I, outside bracket. N minus 1 minus I. Now, what we're going to do is vector string complete. Now, for string A in inside bracket, for string B in outside bracket. Now, string concatenated string is equals opening bracket plus A plus closing bracket plus B. Now, complete sequence equals complete sequence dot pushback concatenated. Now just return complete sequence. Is this clear? Is this clear? So what did I do here? Wrote the base case. One sec. So first of all, is everyone now? So wait, yeah. What did I do here? I wrote the base case. I wrote the base case first. After that, for each inside there can be I. If inside is I, then I cover I with the bracket, and outside I put n minus I. Outside I can put n minus I. Inside bracket is going to be I, size, bracket sequence of length I, of size I, which means length 2i. Outside there's going to be bracket sequence of size n minus 1 minus I. So if A is going to be inside bracket, B is going to be outside bracket, then the concatenated string would be A would be inside the bracket and B would be outside the bracket. Now the total size of concatenated would be n, which means the length would be 2n. Is this clear? Now return the complete sequence now. Now if you if you can look at this closely, this highly correlates with this highly like links up with the way we computed the values. This highly links up with this recurrence. Like initially, for each number in inside bracket, for each number in outside bracket, we are doing this. So the number of times we're going inside this loop, it's going to be inside bracket dot size into outside bracket dot size. Yes, you can call n minus I minus 1 first and then I. That's basically reversing this for loop. Right? You can do that. Anything works. Like that's basically reversing the for loop, n minus 1 to 0 instead of 0 to n minus 1. Like if you look at this closely, a n minus 1 into a0. Or here, since you are going from reverse, a0 into a n minus 1. So the first, when I equals 0, then a0 into a n minus 1 strings would go inside my complete sequence. Because generate I will give you one string, Generate 0 will give you one string, and generate n minus 1 will give you a n minus 1 strings. So totally, a n minus 1 new strings would go into complete sequence in this new sequence. And when I equals 1, then this will give you generate 1. Your order won't matter when you're computing. Generate 1, and this will give you generate n minus 2. Now, Vinay, you think we're missing a? No, we are not missing that, because that would mean double counting. A plus, yeah, we can compute outside bracket first and inside bracket second. But Vinay, we're not missing that, because in A it's already like you're double counting, because in A there could be a opening closing bracket already, and that's already being computed. Then we will be double counting, isn't it? Like A plus, Vinay is asking if A plus opening plus B plus A, and then opening closing bracket, inside that you put B. Shouldn't we count that as well? No, we don't, because we are already, that's already being included in this. For example, if you have here something like this and something like this, A and B, A will also have the first place where it contains this, right? In A, there'll be something here, like A is also computed like this, right? There's an opening and closing inside A. So if we compute this and this separately, A, there will be a lot of double counting if you look at it closely. All right. So this will give you the complete sequence. Any questions so far? Any questions so far? Is it clear? Could you please let me know in the live chat if it's clear? Or if it's not clear, please let me know in the live chat as well. All right. Awesome. 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 That's great. All right. Now you can see that, like, so if you just type Catalan numbers here, you can see how great, how it grows nearly exponentially. Like, I can just show graph. Well, where do I show this? Where's the sequence? Yeah, so you can see the sequence. So Catalan numbers, this is also called Catalan numbers. So the sequence grows really quickly, really fast. Okay, this is just to give you an idea. All right, now doing this, what do you do here? Let's calculate the complexity for calculating AN. How costly is it to calculate AN? How costly is it to calculate AN? Yeah. Oh, sorry. Oh, my bad. Sorry about that half screen. Can you see 1125, and it's going above a million already. It's going 2 million after, like, this is C1, C0, C1, C2, C3, like answer for 3 and so on. And already for A10 or 12, you can see that for A10, the answer is 16,000, and for A20, it's going up to a billion already. So it's like, it's going to be like, it grows really quickly, Catalan numbers. Okay, that was the motive. Yeah, one sec. Yeah. All right. So now, what are we doing now? Let's calculate the complexity of calculating this first. Complexity of calculating this. So for each I, we are going I times, right? For each I, we are going I times. So what would be the complexity for calculating up to n? Can anyone tell me in the live chat? What would be the complexity for calculating up to n? For a given I, it's O of I for calculating. So for all n, how much time would it take? 1 plus 2 plus so on till n. Because for 1 it would take 1, 2 it would take 2, so n it would take n. And we know that this is just n into n plus 1 by 2, which will mean the complexity will be O of n square. Right, O of n square. Yep, it will be O of n square. We can ignore you can ignore n because it grows faster than n square. So it grows slower than n square. So n square is the bottleneck, O of n square. Right. All right. Now how do we do this quickly? How do we do this quickly? How do we compute for all n in O of n? Yeah. So how do we compute all n in O of n? That's where combinatorics comes in. I should probably change the title of this class to Catalan Numbers. Yeah. So it turns out this number an, it has a name to it as we saw previously. An is also called as Cn, for example, and it's called Catalan Numbers. Catalan Numbers. All right. Vinay, I don't. Not every DP question can be generalized into the general formula and get into O1. That's not every time. All right. So some of them can, like if you use a smart observation, but most of them don't. All right. Now you'll be amazed how it can be reduced to a. This is going to be a hard reduction, so it's okay if you don't get it, but try your best attempt to get it. Okay. Like I'll try to explain it in my best way. So, what is what are we trying to find here? The answer for an, where number of bracket sequence of size n, right? One sec, I went out of the frame. Okay. So, Vinay, good to know that. So, yeah, if you attend my classes, you'll get your concepts more clear about this. So, an is the number of valid bracket sequences of size n, right? Okay. Now, what is a valid bracket sequence? We discussed in the starting. What is that? A bracket sequence is valid if number of opening brackets at any point. At any point, the number of opening brackets should be greater than or equal to the number of closing brackets. For example, at this point, at any point, there's an opening bracket here or closing bracket here. Here at this point, there are two opening brackets, 0 closing brackets, 2 opening brackets, 1 closing bracket. So at every point, it should be equal, greater than or equal to the number of opening brackets should be greater than or equal to the number of closing brackets. And in the end, the number of opening brackets should be equal to the number of closing brackets. Is that clear? Sorry, I told that quickly. But yeah, did you get that? All right. Now let's look at a different representation of this. So instead of counting it recursively, we try to find the number of strings of 2 characters. Let's say u and r, u comma r. All right, I'll tell you what it means just in a second. Okay, just a minute. U and r, where at any point the number of if you take r r s r sorry r r u r u u r u. All right, at any point the number of r's is greater than or equal to the number of u's. At this point, you can see at any point in the prefix. For all prefixes, the number of r's is greater than the number of u's. All right. All right. Basically, R is basically an opening bracket. U is a closing bracket. Now, take this grid. You want to go from 0, 0 to 4, 4. What are the number of ways to go from 0, 0, to 4, 4? We know that it is 8 choose 4. 8 factorial by 4 factorial into 4 factorial. We discussed about this in the last class. Why? Because every right, whenever we take a right, we write an R here. Whenever we take an up, we write a U here. The number of ways to do this would be basically arranging 4 R's, basically choosing 4 out of 8 positions for R's, right? M plus NCM, correct. For M, N, it's M plus NCM. For 4, 4, it's 8 choose 4. 4 plus 4 choose 4, right? All right. Sumit, I like using recursion, but it's more memory efficient if you use iterative, but like whichever is convenient to you. Really. Now, the number of ways to go from 0, 0 to 8, 4, 4 is 8 choose 4. Why? We discussed this in the last class. Just stay with me here because this is going to be a bit tricky. You listen with concentration. So, starting from 0, 0 and you're going to 4, 4. At every point, you're taking either a right or an up or maybe 2 ups in a row. That's okay. So this is basically the number of strings of R's and U's where there are strings of length 8, where there are 4 R's and 4 U's. And that's basically 8 factorial by 4 factorial, 8 choose 4 basically. We are choosing 4 positions out of 8 positions to put R's in, and then next, whatever the remaining positions are, we put U's. So from 8 positions, choosing 4 positions is 8 choose 2, 8 choose 4, right? All right. Now, let's draw the grid again. Now, let's look for every opening bracket and closing bracket, right? Instead of opening bracket, we call it right. Closing bracket, we call it up. So here we take right, every right. When we go up, we do a closing bracket. When we go right, we do opening bracket. So we just, so this is opening bracket, closing bracket. If you go up again, it's a closing bracket. If you go right, it's an opening bracket. Go up, closing bracket, opening bracket. So basically, the number of valid bracket sequences, reduces to finding the number of paths where at any point the number of R's is greater than at every point. It's the same definition actually. Number of R's is greater than equal to number of U's. Yes or no? 0, 0 to 4, 4. I'm trying to calculate bracket sequences of size 4, which is every point number of R's should be greater than number of U's, greater than equal to number of U's. Yeah, extra condition. So here we need to find the number of paths with an extra condition. Not before, the number of paths was just 8 choose 4. Now we have an extra condition where the number of R's should be greater than or equal to the number of U's. Correct? Now, how do we calculate this? Like, it seems a bit overwhelming, right? All right. Now, let's check the points where we violate that condition. We go here, the number of right, if you go here, it's fine. If you go here, the number of R is just equal to the number of U's. So if you go here, now there are 2 R's, 1 U. If you go here, 3 R's, 1 U. If you go up, 3 R's, 2 U's. Go up again, 3 R's, 3 U's. If you go up again, there are 3 R's, 4 U's, which we do not want. Alright. So basically, whenever you cross this line, all points, whenever you reach a point on this line, number of R's is equal to the number of U's, because you're taking the number of rights is equal to the number of ups. That's when you reach that line. But whenever you cross this, if you go one step above, you're violating. The number of ups is going to be more than the number of rights. You want to stay below the I, I at every point. As Pavan Agarwal mentioned. Yeah. This is basically the line x equals y if you remember coordinate geometry. So we want to stay below the on or below the line x equals y. Got it? Yeah. So basically, you want to stay below the diagonal. Man, why do I? Oh. Yeah. So we want to stay below this diagonal, on or below this diagonal. Being on this diagonal is also fine, because at this point we go here, say we do this. We get the opening, closing, opening, closing. That's a valid bracket sequence. So if you do anything like this, you can see that you get a valid bracket sequence. If you do this, for example, I'll show you that you'll get a valid bracket sequence. Right, which is basically this, opening, opening, up, closing, right again, opening, closing, closing, opening, closing. You can see that is a valid bracket sequence. If you look at this closely, this is basically this maps with this. It's a valid bracket sequence, right? So every path, if you go like this, for example, one sec. That's basically 4 opening and 4 closing, because you're going 4 right 4 times and up 4 times. So by doing this, you will get every bracket sequence, every valid bracket sequence, isn't it? Every valid bracket sequence. Now, how do we calculate this? How the hell do we calculate this? The number of paths going from 0, 0 to 4, 4 without passing this diagonal, without crossing this diagonal. It should not jump above the diagonal. It should not jump up. So basically, the number of valid bracket sequences of size 4 is equal to the number of paths from 0, 0 to 4, 4 without passing the diagonal. Is this clear so far? Any doubts on this so far? Do you want me to re-explain this? Because whenever you, like, when you reach the end, you can see that the number of ups would be equal to the number of rights, which means opening equals closing. And this new condition is simply telling that the number of ups should never be greater than the number of rights. You shouldn't exceed your budget of ups at any point. Got it? All right. Now comes the hard part. Where you calculate what the answer is. So what we do is, we cannot calculate the answer directly. We can't just say, hey, half of the paths will be below and half of the paths will be above. So the answer is going to be 8 choose 4 by 2. No, this is not going to work because half the paths will be below and half the paths will be above, but there'll be a lot of paths crossing each other too, right? Crossing the line as well. That's why this is the wrong answer. Some of you might think this is the answer, but this is wrong because some paths will be completely below the line, some paths will be completely above the line, but there'll be a lot of paths passing as well. So it becomes a bit complicated, but no worries, we'll solve it. So what we do here is, let's count. So we want to calculate the number of good paths. Basically the number of paths that lie on or below the diagonal. On or below the diagonal. We can also write this as is equal to 2n choose n. So that's basically, sorry, 8 choose 4 minus bad paths. Bad paths means the number of the bad paths is the number of paths that cross the diagonal. For example, this is a bad path. It's a bad path because it crossed the diagonal. Whereas this is a good path. It's a good path because it did not cross the diagonal. Now, how do you calculate the number of bad paths? How do you calculate the number of bad paths? So let's take the first time it exceeded its budget. Let's look at here. So I'll use a generalized method here. Like I'll just ask a first I'll ask a question. Take an n by n grid. So 0, 0, and you want to go till n, n. Can anyone in the live chat tell me, Suraj, 8 choose 4 by 2 is wrong because the number of paths completely below the diagonal will be equal to the number of paths completely above the diagonal. But there are a lot more paths more than this which reach 4, 4, but they cross the diagonal. So 8 choose 4, it's going to be less than 8 choose 4 by 2. So number of bad paths, it's not 8 choose 4 by 2 because it's not that straightforward. So 0, 0 to n, n. Can anyone tell me number of total paths for 0, 0 to n, n? Can anyone just tell me directly in the live chat? I'm just looking at it. Yep, it's 2n, choose n. Fair. All right. Now, what does it mean? What does it mean to go above the line? It means that you're going from, yes, 2 n, yeah. So what does it mean to go above the line? What does it mean to go above the line? It means that you're going to x, x plus 1, where call this as 0, 0, call this as 1, 0, 2, 0. This is going to be 1, 1, 2, 2, and so on. So we need to find the number of bad paths from 0, 0 to n, n, where it never goes above this line, right? Is there a grid? Wait, I think a grid would be useful. I hope I get a grid. Oh man, do we have a grid here? Okay, we don't. No problem. All right. So what are you searching for here? So all right. We never want. Okay, my diagonal is a bit weird, but this is 0, 0. This is say n, n. This is 1, 1, 2, 2, 3, 3, so on. So what does it mean to exceed the budget? Let's look at the first time we exceed the budget. First time we exceed the budget. We want to calculate the number of bad paths. Let's calculate the number of bad paths first. First time we exceed the budget, let's call that as, we go to x, x plus 1, right? So from x comma x, so we need to cross that, we need to reach the diagonal first, right, to exceed it. So first, let's reach the diagonal at x comma x, and then we exceed it. Let x be the first point that we exceed the diagonal. So that point would be x comma x plus 1. X comma x plus 1. Let that be some point. Let this be that point, for example. Now, what we do is, instead of, we're counting the number of bad paths. Now, whatever the path from here to x comma to n comma n, we reflect it. We reflect it. Right? We reflect it. Oh man, yeah. We reflect it. And we'll see what we get. We get all paths going to this here, which is n minus 1 comma n plus 1. If we reflect it. Let's this might be a bit overwhelming to you at start, but I'll tell you what this means here. So what we do first is, let's take a bigger grid. Zero comma 0. We are trying to calculate, say, 4 comma 4. Let's look at all the paths that reach 3 comma 5 first. All the paths which reach 3 comma 5. All the paths which reach 3 comma 5. Let's say this is one path which reaches 3 comma 5. This is one path which reaches 3 comma 5. And let's look at the first time. And this is the, let n equals 4 for now. We'll just look at it. N equals 4. This is the diagonal, right? This is the diagonal. Now, the first time it crosses the diagonal, look at the path from here. If we flip it, we go to 4 comma 4. So every path from 3 comma 5, let's look at the first time it crossed the diagonal. At this point, right? And now from this point, we take an up, we get 3 comma 5. But if we flip it, we get 4 comma 4. Alright. Now this might seem too special a case, so it won't convince you directly. I'll take a more sophisticated case. A more complex case, for example. Let's look at this path. Let's look at this path. Now, note that we are calculating number of bad paths. Calculating bad paths. Okay. Now, this is the first time we are exceeding, we are passing the diagonal. Now from here, let's say we reflect the path. We reflect the path and see where it goes. So we reflect the path. So first we are taking up here. 2 ups, 1 right. 2 rights, 1 up. Up, right, right, up. We are reaching 4 comma 4. So we mirror this path here. Mirror this path, we reach 4 comma 4. So all paths which reach 3 comma 5 are basically are same as the number of bad paths to 4 comma 4. How? It's same as the first time we are violating the condition. From that point, if we reflect the path, we're going to 4 comma 4, right? Aren't we? Are we going to 4 comma 4? So, reiterating this, if you look at this path here, it's clearly violating, and we know that all paths to 3 comma 5 have to pass this diagonal at some point or the other. It has to pass because hey, it's above this diagonal, right? So every path to 3 comma 5, the first time it violates this condition, first time it passes x comma y, first time it passes the diagonal, the path after that, you just reflect it. You get this? You get this? This is a bad path to 4 comma 4. So this is one example. We can take another example too. Okay. Yeah. We can take this example too. We can take this example. No, good paths are not reflections of bad paths. Good paths should be strictly below the line. So good paths and bad paths have very weak relation. So we just compute the bad paths first. Like we forget about the good paths. Good paths have a very strict condition, right? So, and it's very hard to compute them. That's why you're calculating the bad paths. Bad paths is just, yes, Pawan is exactly right. Pawan, that's really smart. Good job. So the first time we cross x comma x, every path that reaches 3 comma 5, it passes through this line, and the first time it passes, if you flip the path, that is, every up you go here, every right, you can take every right. We take the reflection basically. Take the reflection. If we take an up here, we take a right here. If we take a right here, we take an up here. And if we take an up here, we take a right here. We are reaching the reflection of this is basically this, right? We reach 4 comma 4. So the first time we violate, we flip the path and we get all the bad paths. Is that clear? So for any n comma n, okay, let's tell the answer for this. So number of bad paths, and we can also see that every path that goes to 4 comma 4, every bad path that goes to 4 comma 4, for example, let's take this bad path. One sec. Every bad path that goes to 4 comma 4, like for example, let's take this path. Let's take this path. Every bad path that goes to 4 comma 4, let's reflect this path again from here. We take 1 up, 2 rights, right? We take 1 right, 2 ups, the reflection, right? We reach 3 comma 5 magically. It's not magically. I'll tell you why it comes later mathematically. I'm just giving an example for 4 comma 4. So every bad path to 4 comma 4 gives rise to a good path. Every bad path to 4 comma 4 gives rise to any path to 3 comma 5. And any path to 3 comma 5, at the first time it crosses the violates, if we reflect it, we get a path to 4 comma 4. So basically, we get that every path to 3 comma 5 gives rise to bad path 4 comma 4. So basically the number of paths, then we can directly, and the converse holds too. Every bad path from 4 comma 4 gives every path to 3 comma 5, and every path to 3 comma 5 gives every bad path to 4 comma 4. Which means the number of paths to 3 comma 5 is equal to the number of bad paths to 4 comma 4. Is this clear? And which is, then we know that the number of paths to 3 comma 5. Can anyone type it in the chat what the number of paths to 3 comma 5 is? These both are same. What is the number of paths to 3 comma 5? Yep, that's correct. 8 choose 3. So bad paths is equal to 8 choose 3. Yes, 2n choose n minus 1 or 2n choose n plus 1. That's correct. Good paths is equal to 8 choose 4 is basically total minus bad paths. That's it. So good paths is equal to 8 choose 4. Total is 8 choose 4 minus bad paths 8 choose 3. So what did we get here? So good paths of length 4, A4 is equal to 8 choose 4 Similarly, if you look at A3, you will also get 6 choose 4 minus 6 choose 3. And for AN, you'll get 2n choose n minus 2n choose n minus 1. Like if you choose 6 choose 4, which is basically, oh man, I made a mistake. It's the reverse actually. 8 choose 3 minus 8 choose 4. Sorry. That's a blunder. This is 8 choose 4 minus 8 choose 3. This is 6 choose 3 minus 6 choose 2. 6 choose, this is 4 choose, an is basically 2n choose n minus 2n choose n minus 1. You can see that this is basically 6 choose 3 is 6 factorial by 3 factorial into 3 factorial. You'll get this as 20. 20. 6 choose 2 is 15. Is equal to 5. Remember, we got the answer as 5 for length 3s. For length 3, we got the answer as 5. So an is basically 2n choose n minus 2n choose n minus 1. And I'll tell you how we got there. Like how is it true for any n? I'll tell you. So first, for 4, what did we get? The first time we go above, we violate the diagonal rule. One second. First time we violate the diagonal rule. What happens the first time we violate the diagonal rule? We go to a number x comma x plus 1. But we need to reach 4 comma 4. So we need 4 minus x r's and 4 minus x minus 1 u's, right? So from x comma x plus 1 to 4 comma 4, we need 4 minus x rights and 4 minus x minus 1 ups. Now when we reflected this, so what do? We reflected this path and see where we go. So basically ups will become rights and rights will become ups. So from x comma x plus 1, if we take 4 minus x minus 1 rights now, since we are doing the mirror image, like the reflection, rights, and 4 minus x ups, where do we reach? 4 minus x minus 1 plus x is basically 4 minus 1, and 4 minus x plus 1 is basically 4 plus 1, which is 4 plus 1, basically 3 comma 5. For every, we need to calculate for every 1 to 3n, or we'll calculate only for n. I'll get to that calculation part later. So basically, what did we do? We reached x comma x plus 1. The first time we violated the diagonal is basically x comma x plus 1, right? We got to x plus 1 u's and x rights, which means we are at a violated place. And from there we see how many r's we need, 4 minus x r's and 4 minus x minus 1 u's. But now what we're doing, we reflect and see where it's going, and we're proving that we are reaching at 3 comma 5. So 4 minus x minus 1 u's, now we're taking 4 minus x minus 1 r's, and 4 minus x r's, we're taking 4 minus x u's. So so the total number of rights and if you take 4 minus x minus 1 r's, we reach at 4 minus 1. 4 minus x ups, we reach at 4 plus 1, which is 5. Similarly, what we do is, for any n comma n, the first time we'll violate this would be at x comma x plus 1, right? X comma x plus 1. And now from this point, we need n minus x r's and n minus x minus 1 u's, because x plus 1 ups are already taken, x rights are already taken. So for every n, we need to calculate for 1 to 3, or will you calculate only for n? We can do it both ways, but like we can calculate directly for n as well. So I'll get there one sec. So x comma x plus 1, we need n minus x minus 1 u's ups and n minus x rights to reach n comma n. From this point, violation point, bad point. This is bad. Now, if we flip this path, it's basically n minus x flip from here. This would give you here. Flip from here, we get n minus x minus 1 r's and n minus x u's. Vinay, we are flipping that only because to make the calculation easier, because otherwise we can't calculate easily. We are flipping so that we are, after flipping, we are arguing that if we flip, we are reaching n minus 1 comma n plus 1, right? So all flips would reach n minus 1 comma n plus 1. And since counting the total number of paths to n minus 1 comma n plus 1 is easier, That's why you're flipping it. Like, flipping it is easier. Since counting total number of bad paths is easier, with like we're equating it to the total number of paths to n minus 1 comma n plus 1. So this flipping it is, the intuition behind that is a bit tricky. It's like, you just need to work out examples. Like, I don't have a correct intuition like behind it, but so it's basically calculating the total number of paths is easier than the number of bad paths, and flipping would give you the total number of paths. All flips would reach there. How are you getting the 3, 5? So Sumit, one sec. So what as we discussed previously, right? So in this, the first time we violate, we want to count the number of bad paths, but counting the number of bad paths directly isn't easy. So the first time we violate, what we do is, for all paths that we go here, first time we violate, we flip the path. We flip the path and we reach here. This is 4, 4, and this is 5, 3, 5. Flip the path. So say we can take any other path as well, any other bad path. Every bad path will correspond, every bad path to 4, 4. Every bad path to 4, 4. If you flip it at the first violation point, we reach it at 3, 5. The intuition behind it is that every path to 3, 5 will cross the diagonal exactly once, and if you flip it from the first point, it crosses the diagonal, you get 4, 4. So the 1, 1 bijection, which the 1 to 1, what the 1 to 1 thing, which flipping gives, like, works conveniently with our calculations. That's my explanation, Vinay. Is that clear? I mean, I hope it's clear. Like, there's no fixed intuition. I mean, I didn't come up with this on my own either. So, like, it's a pretty creative proof. Like, it takes effort to come up with this proof, I guess. Vinay, we are violating at the first violation because, like, we need to fix it somewhere, right? Like, you can flip it at a later violation, but sometimes there's only a bad path needs to have only one violation to a path to become a bad path. One violation is sufficient. I'm not picking the second or third path because a bad path needs only one violation, and I need to pick some violations. So I'm picking the first violation, right? If a bad path needed to have 2 violations or something, the situation would have been different, but the bad path needs to have only at least 1 violation. So picking the first violation would cover all cases. That's the reason I'm picking the first violation. All right, back to this. So x comma x plus 1. So x comma x plus 1 is the first point I'm violating. From there, I need n minus x r's rights to go to the n comma n, and n minus x plus x minus 1 u's to go to n comma n. All right. Now, if I flip, what happens? I'm generalizing it for n comma n. Where will I reach for n comma n? I want to generalize it, right? For 4 comma over 4, we reach 3 comma 5. For n comma n, you can tell that it reaches n minus 1 comma n plus 1, but I'm just proving it. Okay? Every bad path passes through x comma x plus 1, not x minus 1 comma x plus 1. X comma x plus 1. Pawan, that answer was for you. So n minus x comma n minus x minus 1. If you flip, r's will become u's. So we have n minus x minus 1 r's and n minus x u's. Now what do we get with this? So from x comma x plus 1, instead of n minus x r's, instead of this many r's and this many u's, if we take n minus x if we reverse that is flipping, what do we get? N minus x minus 1 plus x, which we get, here we get n minus 1, n minus x plus 1, we get n plus 1. So if we flip, we always reach n minus 1 comma n plus 1. Can you see that? Yes, counting the bad paths is 2nc n minus 1. Sumitava, that's correct. So this is without flipping, we get n comma n. If we flip from there, we get n minus 1 comma n plus 1. Basically, flipping is basically exchanging r's and u's. Like whenever you go r, you go right in the flipped version. When you go, whenever you go right in the normal version, we go up in the flipped version. Is that correct? Is that convenient now? So n minus x comma n plus n minus x minus 1, r's and u's, we go n comma n. If we flip, we go to n minus 1 comma n plus 1. So all the bad paths to n comma n are one-to-one corresponding. Matlab, if there's a bad path to n comma n, there is we can find a corresponding normal path to n minus 1 comma n plus 1 by flipping at the first thing. First violation, we flip it, and then we get our path to n minus 1 comma n plus 1. So since for every bad path to n comma n, there's a corresponding normal path, like any path, to n minus 1 comma n plus 1, and the converse is also true. Every path to n minus 1 comma n plus 1, if you flip it at the first violation, we get n comma n, right? The converse is also true. So this gives us that the number of bad paths to n comma n is equal to all total paths to n minus 1 comma n plus 1. Is this clear, everybody? Is this clear? So using this, what we get is answer. Yeah. Using this, what we get is this clear, everyone? Could you just state it in the live chat saying it's clear? What we get is n comma n bad paths is equal to, and we know that the total number of paths to n minus 1 comma n plus 1 is 2n. Basically, I'll just write it n minus 1 plus n plus 1. Choose n minus 1, which is basically 2n. Choose n minus 1. And the number of good paths is equal to total number of paths, which is 2n choose n, minus bad paths, which is 2n choose n minus 1. All right. And from here, okay, good to see it's clear. So we know that now, we know that good paths 2n choose n minus 2n choose n minus 1. And from this, if you look at this closely, 2n factorial by n factorial minus 2n factorial by n minus 1 factorial n plus 1 factorial. So if we take 2n factorial by n factorial into n factorial common, 1, this is basically 1 minus n by n plus 1, because n factorial, if you take common here, we get n in the numerator, right? And n plus 1 factorial by n factorial is n plus 1, basically 2n. This is basically 2n choose n into 1 by n plus 1. Is this clear so far? This is the Catalan number of size n for n. So this is basically an equals 2n choose n by n plus 1. Is this clear so far? Is there any part of this that you would want me to re-explain? I'd like to re-explain. Is this clear, everyone? This is very important. Like, of course, you can definitely, you don't need the proof for this. You can just remember Catalan numbers as 2nc n by n plus 1. But, you know, there are a lot of modifications to this. Like, you can solve harder problems by knowing this proof. This reflection proof is the reflection proof. I know, like, if you're listening to it the first time, even when I listened to it the first time, it was really hard for me. Like, I couldn't understand, like, why would you do that? Like, why reflection? But just but the correctness made sense. But like, why did they do this? I had this question too. But once you solve more problems about Catalan numbers or so on, this is the basic idea of Catalan numbers. Like, this is how the proof comes up. Like, you take the first violation point, reflect it, you always reach n minus 1 comma n plus 1, And all paths, you can see that all paths to n minus 1 comma n plus 1 correspond to every bad path to 0 n comma n. And that's where the bad paths come in. And we calculate the bad paths because calculating good paths directly is a bit hard. So that's why you get 2n choose n minus 2n choose n minus 1. All right. Yeah, so the brackets will just be it's just an times. Yeah, brackets will just be an, sorry, an equals 2n choose n minus 1. The number of bracket sequences will just be an, right? We discussed that, yeah. Yeah. So since the number of good paths is 2n choose n by n plus 1, 2n choose n by n plus 1. Number of good paths is this. We know that the number of good paths is just the number of good bracket sequences, right? The valid bracket sequences. So from this, what we get is good paths. This is same to n comma n from 0 comma 0 is equal to number of valid bracket sequences Pawan, I'll just answer that question. Valid bracket sequences with of size n for n, like basically n and n. Did you get this? And you don't need the proof for this. Like you don't necessarily need the proof. Like you can go to the solve problems without the proof, but knowing the proof helped me solve an knowing the proof, like being aware of the proof. The problems with the proof, it was once rated 2300 on Codeforces. Like with the proof, the problems using this proof directly helped me solve a 2300 problem on CF with a lot of ease. With a lot of ease. Got it? Like, and I can show you the problem as well, but it's a bit hard. The problem is probably a bit hard, but hard. Like if you know this concept, you can solve that 2300 problem on CF. And it also got me. A lot of people did not know this proof. That's why they did not solve this problem. But knowing this proof can get you to levels. And it also got me rank 2 in Div 2. Like you can see this problem. Oh, this problem, it might be a bit hard initially, but using this concept, you can do it very easily. This problem, I can put the problem here. It's an E problem. I'll put it in the chat later. It's 1024E. I'll just put it in the live chat. 1204E. So using this concept, like you can solve really hard problems as well in combinatorics. But it doesn't occur as frequent, but when it occurs, yeah, it hits a log. So yeah. All right. Is this clear for everyone? Is this proof clear for everyone? Like, for example, you can also solve problems where what do you say? The number of valid bracket sequences under x equals y plus k, not just x equals y. You can also solve number of bracket sequences under x equals y plus k. For example, that I leave it to you as an exercise. Say valid bracket sequences. Here we number of valid sequences, number of paths not crossing x equals y. That's what we saw now, right? We can also see this line is basically x equals y. Number of paths not crossing this line, for example. I'll leave this to you as an exercise. You need to solve this using the reflection technique. The first time it reflects. I want you to solve this using that. Okay? I want you to solve this using that. Got it? Okay. Now, is this clear for everyone? Is the solution clear for everyone? Any doubts so far? Do you want me to re-explain something? Sumit, Pawan, or anyone? Questions? I mean, this is the question that I practiced right now. Okay, from where do I learn these concepts? So it usually happens when I'm solving problems. When I'm solving problems, sometimes the first time when I try this problem or something, I don't get it. Then I look at the editorial. Then I read the editorial very thoroughly, including the proof as well. When I was a beginner, I used to read the proofs and everything very thoroughly. And then the next time a similar concept comes, see, concepts repeat. Like, it's hard to come up with a new concept on your own as a problem setter or even a standard question. Yes, Vinay, the first violation works for x plus k as well, but you just need to reach x comma x plus k plus 1. That's where, and from there you see where it goes away. You'll probably get something like n choose 2n choose n minus k or something like that. So check it out. Yes, now time to practice. Yep, that's correct. So these concepts, now once, see, concepts, new concepts, coming up with new concepts is really hard. So if you solve a lot of problems consistently, chances are the first time a concept appears, you don't get it. Sometimes you get it, sometimes you don't. And once you look at the editorial, make sure that you get the concept really clear in your head. All right. So coding this is basically, you need to compute 2n Cn by n plus 1. All right. You need to compute 2n choose n by n plus 1. But 2n choose n can be really huge. So what do they? So they ask you to compute 2n Cn by n plus 1 modulo big prime number, say 1e9 plus 7, 10 power 9 plus 7. This could be big, so they ask you to compute this. And we already found out in the previous classes how to compute 2n choose n by n plus 1. We know how to compute 2n choose n. Right, we know how to compute 2n choose n quickly, like using some pre-computation. And 2n choose n into n plus 1, inverse of n plus 1, using the Fermat's theorem, power minus 1, using the Fermat's theorem. We can do this too. So this is basically a into b power minus 1 modulo p. So basically we found the answer as n plus 1. So basically pre-compute factorials. Step 1 is pre-compute factorials. This is O of n. And next step is calculate what 2n Cn is. We did how to calculate binomial coefficients in our previous videos. I think in my previous video itself I calculated it. And then let this be a, and n plus 1 equals b. Now we need to calculate a into b power b inverse modulo p. P is given in the input. And now b inverse is just b power p minus 2 using Fermat's theorem. B inverse equals b power p minus 2 modulo p. So we basically need to do a into b power p minus 2 modulo p. If you have seen my previous videos, you know what this means. Fermat's theorem, and this is just a by b, a into b inverse. Now a into b power p minus 2 modulo p. That's it. That's what we are done. Like a into b power p minus 2 modulo p. And for a given n, you can compute this in O of n. But say there are about 10 power 5 test cases, and for each test case we need to calculate for nn. That can be done for each test case in O of log n. For each test case, because computing b power p minus 2 is O of log p. I mean log p or log n. It's not much not very different. Each test case you can compute in O of log p. There's a way you can do it in O of 1 as well, but that's a bit complicated. I won't go into that. O of log p. Because you've pre-computed O of n pre-computation, and for each computation, calculating 2n choose n is just 2n factorial by n factorial into n factorial. You can do this quickly by using the inverse method. to n factorial into n factorial power minus 1 into n factorial power minus 1 into, and by n plus 1, for by n plus 1 you do n plus 1 whole power p minus 2, which is again inverse. Is this clear so far? Any doubts? Any doubts? Do you have any doubts? Do you want me to re-explain anything? Is there anything, any part of it which you want me to re-explain? Do you want me to re-explain like how something came here? Like, do you want to re-explain again? I can explain it to you. Sumit, clear? Vinay, Vikash, I can see a lot of people here. Like, I'd like you to know the proof because, again, as I said, knowing the proof for this like helped me solve a 2300 rated problem, and it got me rank 2 as well, which suggested that a lot of people didn't know the proof for this. Like, and the proof is, it's not like I didn't have to come up with the proof on my own. It was already there. Like, it was there. Like, whenever I was learning what Catalan numbers is, I learned what the proof is as well, and it helped me get that rank. So, I mean, not to boast, but like, I'm just telling you the importance of what the thing is, how important knowing proofs is. Yeah. Just knowing the proof was sufficient. All right. So if it's not clear, drop it in the comments which part is not clear, or rewatch the parts which are not clear in the video, and I hope that will help you. All right. And in the next class, I'll be teaching next class as well. I'm going to teach an important topic in combinatorics. And all right. See you in the next class then. Until then, yeah. I think it's tomorrow. Next class is tomorrow. So it's going to be there at the same time. And if you haven't subscribed to it already, please do subscribe and share it with your friends if you think it's going to be useful. Vinay, after maths, the next topic is going to be DP. So yeah, DP and upsolving. I'm going to do both of them. All right. All right then. See you folks.